Hello everybody, and welcome to our video on double integrals in polar coordinates. So, as we've seen before, some regions are easier to describe in polar coordinates, but they are also easier to integrate over in polar coordinates. So let's just look at a couple descriptions of regions like this as a reminder. So consider the disk with radius 1, that is the set of points inside and including the curve, described by x squared plus y squared equals 1. So this would be actually a fairly difficult region to describe if we were going to integrate, because we would have to do something like y equals plus or minus the square root of 1 minus x squared and have things bounded between those two radicals. So that could be pretty difficult to integrate over depending on the function that you're dealing with. But in polar coordinates, this region is described simply by the set of points whose radius is between 0 and 1, and for which theta is between 0 and 2 pi. So that's a pretty easy description. And it bounds our radii and our angle here by constants instead of having to deal with function bounds, like in this case. So similarly, if we look at this region here, which is the region between the semicircles of x squared plus y squared equals 1 and x squared plus y squared equals 4, and also including these gaps here from 1 to 2 and negative 1 to 2. So that region can be described quite easily in polar coordinates as r is between 1 and 2, and theta is between 0 and pi. So again, much simpler representation here than this. In this case, not only would we have a top function and bottom function, so we'd have to describe things as like y equals plus or minus square root of 1 minus x squared, and 4 minus x squared square root. Then also, we wouldn't have just type 1 integrals here. We'd have to separate this into like 4 different regions to get type 1 and type 2 integrals. It'd become much more complicated. On the other hand, in polar coordinates, the region itself is pretty easy to deal with. So as a reminder, r squared equals x squared plus y squared. That's just the Pythagorean theorem. R is our radius out from the center. So you form a right triangle, and your x and y coordinates are the legs. So x squared plus y squared is r squared, and x is r times cosine of theta, and y equals r times sine of theta. So what we want to do is construct a double integral formula for polar coordinates that will solve the same problems that we would be doing with our regular double integrals. So first, definition we call regions of the form of, and lots of silly typos, of the form r equals r theta, where r is between a and b and theta is between alpha and beta, polar rectangles. So, and if we draw this out, what do we get? If theta is equal to alpha, that's just the straight line passing through the origin, looks like this. And when theta equals beta, that's this straight line. And if the radius equals a, that's just this curve here. And if the radius equals b, that's this curve. So this region here we call a polar rectangle. So obviously, it's not an actual rectangle, but we describe this in polar coordinates in the same way we describe a true rectangle in Cartesian coordinates. Right? Each variable is just between two constant values. So we can divide these intervals, a, b, and alpha, beta, into n subintervals, which give us subrectangles of the following form. So if you look at this picture here, all we've done is just drawn some more angles and some more radii here. And so we get all these different subrectangles. And so these would be the set of all points. Each subrectangle is the set of all points between two subsequent radii and two subsequent angles. Now the center of each subrectangle is just going to be given by the average radius and the average angle. So you take the two subsequent radii, add them together, divide by 2, Take the two angles, add them together, divide by 2. That's going to find you your midpoint for each subrectangle. And since we know that the area of a sector of a circle has area 1/2 r squared times theta, therefore the subrectangle is going to have that area for the larger radius minus the area for the smaller radius. So let me see if I can draw a quick sketch there to make sure that's clear. So here, we've got a subrectangle. So you take the area of the sector of the circle that we're highlighting in yellow here, that's this, and you're subtracting the area of the smaller circle sector here. And when you subtract those two areas, what do you get left? You get left just the area of the polar rectangle. So 1/2 times r sub I squared times delta theta sub j minus 1/2 r sub I minus 1 squared times delta theta sub j. Factor out the 1/2 and the delta theta. We get ri squared minus ri minus 1 squared. And this is a difference of squares, so we can factor it. Ri plus ri minus 1 and ri minus ri minus 1. And now if I divide this ri plus ri minus 1 over 2, that's the average between the two radii, or r sub I star, as we defined up here. And if we look at this expression, ri minus 1, that's just the difference between each r value. So we can call that delta r sub I. So in other words, our delta for our area is equal to r delta theta. So we can replace a Cartesian Riemann sum like this, f of xy delta a sub ij, with f of x in polar coordinates and y in polar coordinates, times r delta theta. So that's in Riemann sums, take the limits, yada, yada, yada. We've been through that routine before. So let's just move ahead here to summarizing this. So if f is continuous on a polar rectangle R, given by R being positive and between A and B, and theta being between alpha and beta, where beta minus alpha is between 0 and 2 pi, that just means the total angle you're rotating through is less than 2 pi. Then your double angle over R of f of xy dA equals the integral from alpha to beta times the integral of the integral from A to B of f of r cosine of theta, r sine of theta, times r dr d theta. So the key here is that you're replacing dA with r dr d theta, and you're replacing x with r times cosine of theta, and y with r times sine of theta. So anytime you have a function in Cartesian coordinates over some region, if that region can better be described with polar coordinates, then you can just convert this integral into this polar form. Okay, so that's pretty much the key idea here. One thing that might help you remember the key part of the change, dA equals r dr d theta, is if you draw this little polar region, you can think of this side of the polar rectangle as being dr, and this side of the polar rectangle as being r times d theta, right? Because that's the length of this segment of a circle. And you find that length by taking the radius of the circle times the angle that's intercepted by that segment, I should say, or that arc. So if you multiply this together, you get r times dr times d theta equals dA. So that may be a helpful visualization. Okay, let's take a look at a question here. Find the volume of the solid bounded by the plane z equals 0 and the paraboloid z equals 1 minus x squared minus y squared. So since this is bounded by the plane z equals 0 on the paraboloid here, we're going to have to plug in z equals 0 into our paraboloid to find our xy region. So this gives me x squared plus y squared equals 1 is the intersection of the paraboloid and the xy plane. And that's just the circle with radius 1. So if I want to integrate over the circle, I can just consider this r between 0 and 1. And theta between 0 and 2 pi. So now when we go to change our function here, it's going to become f of r times cosine of theta, r times sine of theta, times r d theta. And we're integrating with respect to r first, so this will be 0 to 1, and 0 to 2 pi. So we plug in place of x, r times cosine of theta. We get 1 minus r squared cosine squared of theta. And then we plug in place of y, r times sine of theta. So this is minus r squared sine squared of theta. All of that's going to be multiplied by r dr d theta. Now, if I factor r squared out here, negative r squared, I should say, I'll get 1 minus r squared times cosine squared plus sine squared, which is 1. And now if I distribute this r, I get r minus r cubed, dr d theta. And now we can start integrating this. So there's a little bit of setup work to do, but once we start doing this integral, we'll see it's pretty easy. Not a bad integral at all. Okay, so we're evaluating this from 1 to 0. So when I plug in at 1, I get 1/2 minus 1/4, which is 1/4. When I plug in 0, I just get 0. So this is 1/4 d theta. That gives me theta over 4, evaluated from 0 to 2 pi. And that's just going to be pi over 2. All right, that's it for that one. So let's go ahead and move on to a little fact here. If f is continuous on a polar region of the form d equals the set of points r theta, where theta is between alpha and beta, and r is between h1 of theta and h2 of theta, then the double integral of f over d with respect to a is the integral from alpha to beta of the integral from h1 to h2 of f of r cosine of theta, r sine of theta, r dr d theta. So nothing crazy here. We're just saying that if r can be described instead of as being between two constant values, as being between two curves dependent on theta, then we can still integrate the same way, just using those curves as our bounds. So this is essentially the same kind of thing we were doing with regards to Cartesian double integrals. Now, I want to point out one little fact here that's kind of interesting. If we set this h1 of theta equal to 0, then what do we get? Well, the area of the region D we know is equal to the double integral over d of 1 dA from our previous fact. And so if we put that in polar coordinates, we get the integral from alpha to beta of 0 to h of theta, r dr d theta. When we integrate r here, we get r squared over 2. And when we evaluate it at h, that gives us h of theta squared over 2 d theta. So in other words, the area of a general region D bounded by theta equals alpha, theta equals beta, and r equals h of theta is the integral from alpha to beta of 1/2 h of theta squared d theta. Okay. Let's go ahead and move on to another example. So find the volume of the solid that lies under the paraboloid z equals x squared plus y squared above the xy plane and inside the cylinder x squared plus y squared equals 2x. Okay, so the first thing we need to do is figure out what this cylinder is describing precisely, because, we have an equation for it, but it's not quite in a form that's easy to interpret here. So I see that if I rearrange this and have x squared minus 2x, I'll leave 2 blanks here, plus y squared equals 0. That looks like 2 polynomials of x and y, and I could probably complete the square here. So this is b is 2, divided by 2 is 1, and squared is 1 squared. So this gives me, if I factor this thing, x minus 1 squared plus y squared. Here we've got minus 1, but if I add it to the other side, I get 1. So in other words, no matter what the value of c is, this looks like the circle centered at 1, 0. With radius 1. So what does this region look like? All right, so here, this is a cylinder. So it looks like this circle on the xy plane, but of course it's a cylinder, so it goes all the way up and down. But all we need is the image on the xy plane, so we know what we're integrating over. So this is the image on the xy plane. And we know where it's centered. Now, how do we convert this to polar coordinates? Well, it's actually pretty straightforward. You can kind of visualize and see like your angles are going from negative pi over 2 to pi over 2, or from 0 to pi if r becomes negative. So that requires us knowing what r looks like. Well, how can we describe this region in terms of r? So that might become the better question. Well, you may recall that this boundary here, when we talked about polar coordinates, looks like r equals 2 cosine of theta. But if you're a little rusty on that, that's okay. You can actually check this yourself by just plugging in x equals r times cosine of theta and simplifying this equation, and what you'll end up getting is r equals 2 times cosine of theta. Okay, so if r is between that boundary and 0, what does that tell us about our angle theta? So if r is, when is r going to be 0? That's going to be at cosine of pi over 2. So that's halfway through here. Okay, so what do we get here at 2? Well, r is equal to 2 when theta is 0. Cosine of theta is 1 times 2 is 2. So if we start at 0, we rotate through here, we'll get r equals 0 once our angle is pi over 2. And then r becomes negative once our angle is bigger than pi over 2. And so it starts going this way. And when does it stop? Well, it's going to stop at pi, which should make sense because our radius should be -2 when we have cosine of pi. So that gives us our description for our region. And now it's just a matter of setting up our integral to actually evaluate this thing. So we're starting with the integral over d of f of xy dA. And we want to write this as the integral from 0 to pi for theta, 0 to 2 cosine of theta for r. And we're going to replace x and y in our function with r times cosine of theta squared. Right? This is x squared, so r cosine of theta squared becomes r squared cosine squared of theta, plus r squared sine squared of theta, times r dr d theta. Now, if we factor out this r squared, we're going to get cosine squared plus sine squared, which is 1. So we just have r squared times r. So this is r cubed dr d theta. Integrate this, we get the integral from 0 to pi, r to the 4th over 4, evaluated from 0 to 2 cosine of theta, d theta. Okay, 2 to the 4th power is going to be 16 over 4 times cosine to the 4th power, d theta. So this is 4 times the integral from 0 to pi. Now to evaluate cosine to the 4th power of theta, I need to use a power reduction formula twice. So I have to treat this as cosine squared squared. And then cosine squared of theta is going to be 1 plus cosine of 2 theta over 2 squared. Now, 2 squared in the denominator is going to give me 4. 4 over 4 cancels. So this becomes 0 to pi of this numerator squared, which is 1 plus 2 cosine of 2 theta plus cosine squared of 2 theta. Cosine squared of 2 theta, I can apply the power reducing formula again, and I get 1 plus cosine of, now we got to double this, 4 theta over 2 d theta. 1 plus 1/2 becomes 3/2 plus 2 cosine of 2 theta plus cosine of 4 theta over 2 d theta. And now we should be able to integrate this thing. So 3/2 is going to be 3/2 times theta plus 2. The integral of cosine is going to be sine of 2 theta divided by 2. So those 2's will cancel, plus sine of 4 theta divided by 4, which we've already got a 2 there, so that becomes 8. Evaluated from 0 to pi. So this becomes 3/2 times pi, so 3 pi over 2. Plus sine of 2 pi, which is 0. Plus sine of 4 pi, which is 0. Minus 0, 0, and 0. So this is all just 3 pi over 2. All right, so that's it for that example. Let's go ahead and move on. Oh, wait, there's nothing to move on to. That's the end of this section. All right, thank you for watching. Have a great day.